This video is going to be about the independent Boson model, which is one of the systems that we look at in open quantum systems, a simplified version of the spin boson model. And we'll find out soon that the reason why we're so interested in it is because it's actually an analytically solvable model, which is nice. It means that we can use results from this model which are analytically exact, and we can test different approximate methods that we might come up with. Like, for example, we use the reaction coordinate mapping, and we can test how well that approximate method works compared to this analytic model. And then if it works well, we can say, okay, well, maybe our approximate method will work on a non-analytically solvable model like the spin boson model. And the main references we're going to look at are these two textbooks by Schlosshauer, I think that's pronouncing it right, and Petruccioni, these sections in particular. And then I also use quite a famous paper by Glauber from 1963 about coherent state representation of quantum states. So because there's quite a lot of detail in the two textbooks that I mentioned at the start, I'm just going to skip through quite a few things, but obviously what we need to start with is the total Hamiltonian of the system. So we've got some two-level system coupled to a bath of harmonic oscillators, and we're going to have, it's basically just the spin boson model Hamiltonian without the tunneling term, so there's no sigma x term in the system Hamiltonian. And we're going to keep things super general, and we'll allow the coupling coefficients to be complex. And then we'll have the Hamiltonian of the bath itself. So here's our system part. We've just got epsilon over 2 times sigma z. We've got the coupling term, the interaction term, which has the sigma z of the system coupling to the what is essentially the position coordinate of each mode of the bath. And then we've got the self-Hamiltonian of the bath, where we've ignored the 0 point energy. So sometimes you'll see like a plus half here as well. But we're not going to include that. So physically, what this kind of looks like is we've got a two-level system with some ground state energy and some excited state energy, and we're saying that the splitting between that is what we call epsilon. And then this is coupled to a bunch of different harmonic oscillators. So I'll just draw 3 for now. So these are separate harmonic oscillators. So maybe this is k equals 1, k equals 2, k equals 3. So that's what these labels are here. And it's coupled with some particular strength. So this will be strength G1, strength G2, and G3 to this one. And then if I zoom in on what one of these oscillators might look like, it's just going to be a quantum harmonic oscillator with particular energy splitting, which in this case for k equals 1 is just going to be omega 1. And then say this would be the case where there's 0 excitations in the boson, 1, 2, and so on. Okay. So as always in open quantum systems theory, the thing that we're going to try and find is the interaction Hamiltonian in the interaction picture. And what this basically, a way I like to think about this is we just unwind the we unwind the dynamics due to the self-Hamiltonians of the system in the bath around the interaction Hamiltonian. And what do I mean by unwind? Well, if we think about if I've got some Hamiltonian, then the time evolution due to this is going to look like this. So the opposite of that is just going to be with a plus sign here. So that's why, unlike in the case how we normally transform operators, we would have the minus sign here and the plus sign here. It's just the opposite way around because we're kind of unwinding the self-Hamiltonians of the system and bath, the evolution caused by those two things. So this interaction Hamiltonian is going to look pretty similar to the original interaction Hamiltonian, except the bosonic operators are going to pick up complex exponentials that look like this. And the reason that the sigma z stays the same is because the sigma z commutes with the self-Hamiltonian of the system because it's just proportional to sigma z. So things are nice and easy in this case. Okay, so we've just got sigma z tensored with sum over all the modes of gk with bk dagger, so a creation operator, with a complex exponential e to the I omega kt, and then basically just the complex conjugate of that entire thing. Okay, so this is just equal to the thing that we wanted, which was the interaction Hamiltonian in the interaction picture. So now that we've got the interaction picture in the interaction Hamiltonian in the interaction picture, we can use that to find the time evolution in the interaction picture. And then from this, we can find out all the dynamics that we need to find, which is nice. And the reason that all works is because everything that we want to find is going to be using some trace. So we're going to end up tracing a bunch of operators with a quantum state. So it doesn't really matter if we're in the interaction picture or the Schrodinger picture. So we can find the dynamics in the interaction picture and everything's all good. So basically it turns out that this thing, as it currently stands, is quite complicated, and it's due to this time ordering super operator that goes in front of this exponential here. So this is basically what happens when you have a time dependent Hamiltonian and you're trying to exponentiate it. So we've got some dummy variable s here, and we're going to integrate over all these Hamiltonians from 0 to t. And then we need to time order them all. So basically what that means is that we're going to need to swap some of them around. And whenever we swap operators around, we need to think about the commutator. And thankfully, the commutator of this particular interaction Hamiltonian at two different times isn't an operator, which would make things difficult. It's actually just a complex number, which is nice. So the commutator of this interaction Hamiltonian at two different times is just equal to this particular complex number, which is good because the commutator of this with an operator is just going to be 0 because it's just a complex number. Okay, so what this nice little form of the commutator allows us to do is it allows us to write this time evolution operator that's in the interaction picture in a much nicer form, and it's just got some global phase at the start that we're not going to care about, so let's just ignore it for now. And then we've got some exponential with a sigma z over 2 tensored with something that looks kind of similar to what we had in the interaction Hamiltonian, except now we've got some time dependent coefficients and there's a minus sign between the creation and the annihilation operators instead of a positive sign. And I'll quickly just write down what this alpha k of t is. So it's going to be 2 times the strength gk divided by the mode frequency omega k multiplied by 1 minus e to the I omega kt. And we find this here by actually solving this and using this commutator. But that's quite long to do, so I'm going to completely skip it. You'll just have to trust me. So if our time evolution in the interaction picture looks like this still isn't super helpful. It looks fairly complicated still, so I'm going to show how we can write it in a much nicer way. Just bear with me. Alpha kt star times bk. So if we notice that everything on, say, after the sum over k belongs to the Hilbert space of the bath, and the sigma z belongs to the Hilbert space of the system. So let's just write that out because I quite enjoy writing those h's for the Hilbert space. So then bk belongs to the Hilbert space of the bath. So what does that mean? Well, it means that the two of them commute. And what that means is that I can write v of t as x times sigma z, and I'm just going to call everything else, so everything here, and I'll take this factor of 1/2 too, and I'm just going to call it some operator b. And then what I can do is I can expand this exponential, k equals 0 to infinity, sigma z times b to the power of k over k factorial. And now I can expand this exponential out, and I'll use the fact that sigma z to any even, so let me rewrite that, so sigma z to any even power, so 2 to the n where n is some integer, is going to equal the identity. And I'll rewrite this as the identity plus sigma z times b plus 1 over 2 factorial identity times b squared plus 1 over 3 factorial sigma z times b cubed, and so on. And now what I'm going to do is I'm going to write the identity in the sigma z basis, so it's going to be EE plus GG. And then I'm going to write sigma z as EE minus GG. And now what I'm going to do is I'm just going to replace all the identities with EE plus GG, and I'm going to replace all the sigma z's with EE minus GG, and then I'm going to collect all of the EE terms and all of the GG terms. So when I do all that, I collect the EE terms and I see everything that's multiplied by EE, and what I get is identity plus b squared over 2 factorial plus b cubed over 3 factorial, and so on. And then I collect all the GG terms, and what I find is identity minus b plus b squared over 2 factorial minus b cubed over 3 factorial, and so on. And what this is EE times exponential of b plus GG times exponential of minus b. So this is a much nicer form for our time evolution operator. And I'm being lazy here, and we should remember that this operator b is actually time dependent because of the alpha k's that are involved. But anyway, I'll zoom through this now, and EB, if I remember what b is going to be exponential of a half sum over k alpha kt bk dagger minus alpha k star of t bk, and this thing here is just the displacement operator. Displace by alpha k over t divided by 2. And that means that e to the minus b is just displace by minus alpha k of t over 2. So that lets me write this time evolution operator in a very instructive form, which is EE tensor. There's one thing I've forgotten here. So this sum over k, because all of the different modes commute with each other, ends up becoming a product here. So we've got EE tensor, the product of displaced mode k by amount alpha k over t of t over 2, plus GG tensor pi k, so the product of all the displacement operators by minus alpha k t over 2. So what's happening is we're going to displace each mode of the bath by either alpha k t of t over 2 or minus alpha k t over 2, depending on the state of the system. Now we found a nice form of the time evolution operator in the interaction picture, which is displace each mode k in the bath by an amount alpha k over 2 if the system is in the excited state, or displace it by an amount minus alpha k over 2 if it's in the ground state. And then we also need to remember that these displacements are time dependent too. So now that we've got this, we can find the reduced state of the system, which is going to be the thing that we're actually interested in. And how are we going to do that? Well, the reduced state of the system is just going to be the trace over the bath degrees of freedom of the entire time-dependent state. And the time-dependent state is going to be given by, well, the initial state that's been evolved by this time evolution operator. So that's going to be what we'll call that rho naught, and we'll call this v dagger of t. And notice that v dagger of t is just going to be exactly the same as v of t, except the displacements are going to have opposite signs. So with the EE there's going to be a minus sign, and with the GG there's going to be a plus sign for v dagger. Okay, so let's say that the initial state of the system in the bath is factorized, which is a nice assumption that we usually make, the Boson approximation. And let's also assume that the bath is in a thermal state. So one thing that's nice about the independent boson model is the fact that the system Hamiltonian commutes with the interaction Hamiltonian. And that it just implies that the system Hamiltonian commutes with the entire Hamiltonian, because it obviously commutes with itself and it also commutes with the Bath Hamiltonian. So it's a little bit redundant to say that, but this is a nice way to think about it, because this tells us that the system Hamiltonian doesn't change in time, because the time dependence of the operator is proportional to its commutator with the total Hamiltonian. So what this means is that the expectation value of the system Hamiltonian doesn't change in time. So what that means is that there is no exchange of energy between the system and the bath. And what we also know from the fact that there are no terms within the Hamiltonian that look like EG or GE, it means that the populations in the system density matrix are constant in time. So what's that going to mean? Well, for us, what it means is that there's one less calculation to do, because we know that the diagonal terms of the system density matrix are just going to equal their initial values. Where this notation that I'm writing here, the superscripts, let's just say IJ, just mean the matrix elements. So we'll take the EG element of the system density matrix. How do we find that? Well, let's sandwich E with what rho S of T is. Well, rho S of T is the trace of the bath of the entire time-dependent state. And if we just insert everything here, I also forgot the G on the end. If we just insert the nice form of V of T and V dagger of T, then what we'll find is that this becomes something quite nice. So we still have the initial state, the initial value of the EG matrix element, but it gets multiplied by a trace of a displacement operator with a thermal bath, with another product of there should be a subscript K there, with another product of displacement operators. And this is, it looks difficult to find, but what we do is we just write the coherent state in the coherent state representation, which is also gets called, I think it gets called the Glauber P rep. And the reason that we do that is because the coherent states are eigenstates of the displacement operator, so it just makes it much nicer to use. And essentially what we find is that these diagonal elements of the reduced system density matrix look like this. So we have an exponential of an integral of the bath spectral density function multiplied by some temperature dependent term with some oscillations too. So essentially what this tells us is that the diagonal elements of the density matrix are going to decay exponentially, but they're also going to oscillate. So maybe it might look something like this. If we imagine this is say like the coherence as a function of time. So there we have it. We've got all of the elements of the reduced system density matrix as a function of time. The diagonal elements are just equal to their initial values because of the fact that there's no energy exchange between the system and the bath, and also because there's no EG or GE terms in the Hamiltonian, so the Hamiltonian can't change those diagonal elements. And then the off-diagonal elements are again proportional to their initial values, and then they have this exponential, which is some sort of decay and oscillation, which depends on the spectral density of the bath and the temperature of the bath. And then because of the way the density matrix work, we only need to calculate one of these diagonal elements, and then the other one is just a complex conjugate of it. So that's been a fairly quick and brief introduction to the independent boson model. So as I said at the start, the reason why I'm interested in this model is because of the fact that it's analytically solvable, and what it's letting me do is test a method of probing heat statistics and work statistics. So I'm using this reaction coordinate mapping together with full counting statistics, and by looking at the independent boson model, I'm able to test how well my I don't really want to call it a theory, but the way that this calculation technique works, because I already have the answer in the independent boson model. So if I get the right answer with my method, then that gives me some confidence that I can use it in more interesting models like the full spin boson model that doesn't have an analytical solution. So that's why I'm interested in the independent boson model, and hopefully this video is useful. If not for anyone else, then at least for me, if I come back in a few months to look over this. So yeah, thanks for watching.